Close your eyes for a moment and imagine standing beneath a sky that dances with light. Ribbons of green and violet flowing like celestial curtains across the darkness. This is the Aurora Borealis, the Northern Lights, and tonight we'll journey together through their story. Long before we understood what caused these lights, humanity looked up in wonder. The very name Aurora Borealis carries within it the poetry of ancient understanding. Aurora was the Roman goddess of dawn, who renewed herself each morning and flew across the sky to announce the coming of the sun. Borealis comes from Boreas, the Greek god of the north wind. Together, these words paint a picture. The dawn of the north, a perpetual sunrise dancing at the top of our world. But humans have watched these lights for far longer than the Romans or Greeks walked the earth. Evidence suggests that our ancestors witnessed auroras as far back as 30,000 years ago. Cave paintings in southern France, created during the last ice age, when the climate was much different, may depict these celestial displays. Imagine those early humans, wrapped in furs, watching the sky ignite with unexplainable fire, wondering if the heavens themselves were alive. The indigenous peoples of the far north developed their own profound relationships with these lights. The Sami people of northern Scandinavia believed one must be quiet and respectful when the lights appeared. They taught their children never to wave, whistle, or sing at the aurora, for fear of attracting its attention. To them, the lights held power that demanded reverence, a force of nature as real as thunder or wind. Across the ocean, the Inuit peoples carried their own understanding. Some Inuit communities believed the lights were spirits of the dead playing a ball game across the sky, using a walrus skull as their ball. Others saw them as torches, held by spirits to guide the souls of the recently departed to the land of brightness and plenty. In their worldview, the aurora connected the living and the dead, earth and sky, in an eternal dance. The Cree people offered yet another interpretation, one that speaks to the interconnectedness they saw in all things. They believed the northern lights were the spirits of their ancestors, attempting to communicate with the people on earth. When the lights were particularly bright and active, it meant the spirits were happy and dancing. This wasn't superstition to them. It was recognition of something profound overhead, something that bridged worlds for thousands of years. These lights remained firmly in the realm of mystery and mythology. It wasn't until the 17th century that European science began to seriously document and study them. The French scientist Pierre Gassendi gave the phenomenon its lasting name in 1621, drawing on those ancient Roman and Greek deities to describe what he witnessed in the skies over France. His naming was an act of translation, taking something otherworldly and grounding it in classical knowledge, making it something that could be discussed, recorded, and eventually understood. Yet even as science turned its attention to the aurora, the lights kept their mystery. Throughout the 1700s, observers noticed something curious. The auroras seemed to follow patterns. They would appear more frequently during certain years, then fade to rarity, then return again in what seemed like a rhythm. This was one of the earliest clues that the northern lights were connected to something beyond our Earth, something cycling and vast. The indigenous wisdom and the emerging scientific curiosity were describing the same phenomenon from different languages of understanding. Both recognized that these lights were not random, not merely beautiful, but part of something larger. The Aurora Borealis was a messenger, whether from the spirit world or from the sun itself, telling us that our world is connected to forces beyond our immediate perception. And so we begin our journey here, at the intersection of ancient wonder and modern understanding, ready to explore how these dancing lights above us are born from the very heart of our sun, traveling millions of miles to paint the polar skies with colors that have captivated humanity since the very beginning. Let us continue deeper into their story. As the 18th century gave way to the 19th, a revolution in understanding was about to dawn. The Northern Lights were no longer just a mystery to be wondered at. They were becoming a puzzle that science could begin to solve. In 1741, Swedish astronomer Olof Peter Hyota made a curious discovery. He noticed that whenever the aurora appeared in the sky above him, his compass needle would dance and waver, as if disturbed by an invisible hand. Here was the first concrete evidence that the lights were somehow magnetic in nature, that they were connected to the same forces that guided sailors across oceans. The aurora wasn't just like ... it was magnetism made visible. But the true breakthrough came from an unexpected place. In 1859, the Sun released what would become known as the Carrington event, named after British astronomer Richard Carrington, who witnessed a massive solar flare through his telescope. That brilliant eruption on the Sun's surface sent a wave of particles racing toward Earth at unimaginable speeds. When they arrived, the Northern Lights appeared as far south as the Caribbean, painting skies that had never seen such displays. Telegraph systems around the world sparked and caught fire, their operators receiving shocks from the electromagnetic storm. Some telegraph lines worked without any power at all, driven by the auroral currents themselves. This catastrophic beauty revealed something profound. The Northern Lights were born from the Sun itself. Every aurora begins 93 million miles away, in the roiling, nuclear heart of our closest star. The Sun doesn't burn the way a fire burns. It transforms matter into energy through nuclear fusion, and in doing so, it constantly releases a stream of charged particles into space. Scientists would come to call this the solar wind, an invisible river flowing outward from the Sun at speeds of roughly 1 million miles per hour. Imagine it, a constant breath exhaled by our star, washing over everything in the solar system. This solar wind is composed primarily of electrons and protons, the fundamental building blocks of atoms, stripped away from the Sun's atmosphere and sent streaming through the darkness. Every second, the Sun loses about 1 million tons of its mass to this wind, and yet it's so vast that this has barely any effect over billions of years. When this solar wind reaches Earth, traveling 4224 days across the void of space, it encounters our planet's magnetic field. The Earth is, in essence, a giant magnet, with magnetic field lines stretching far out into space, creating an invisible shield called the Magnetosphere. This shield extends roughly 40,000 miles on the sun-facing side of Earth, and stretches out more than 200,000 miles on the night side, forming a vast magnetic tail that points away from the Sun. Most of the solar wind is deflected by this magnetosphere, flowing around our planet like water around a stone in a stream. This is what protects us, what keeps our atmosphere from being stripped away into space, as happened long ago on Mars. But some particles, particularly during intense solar activity, find their way into the magnetosphere through weak points near the magnetic poles. These are the gateways where the magic happens. As these charged particles spiral along the Earth's magnetic field lines, they're funneled down toward the polar regions. Picture countless electrons and protons sliding down invisible highways in the sky, accelerating as they descend toward the upper atmosphere. When they finally collide with gas molecules in our atmosphere, approximately 60 to 200 miles above the Earth's surface, energy is transferred in these collisions. The atmospheric gases become excited, literally, in the scientific sense. Their electrons jump to higher energy levels. But this excited state cannot last. Within moments, the electrons in these atmospheric atoms drop back down to their normal energy levels, and when they do, they release the absorbed energy as light. This is the aurora, photons of light released by oxygen and nitrogen atoms returning to their ground state after being energized by solar particles. It's the same principle that makes neon signs glow, but painted across the sky on a canvas hundreds of miles wide. The colors we see tell us which gases are being excited and at what altitude. The most common color, that ethereal green that features in countless photographs, comes from oxygen molecules about 60 to 150 miles up. This particular shade of green is oxygen's signature, the wavelength it prefers to emit when excited by solar particles. Higher up, above 150 miles, oxygen produces a rarer deep red aurora. These high-altitude red auroras are less common because the air is so thin up there that collisions happen less frequently. And so we begin to see the full journey, from the nuclear heart of the Sun across the vast emptiness of space, through the Earth's magnetic shield, down invisible field lines to the polar skies, and finally the collision with our atmosphere that creates those dancing lights. Every aurora is a visible connection between our world and our star, a reminder that we live not on an isolated planet, but within the Sun's embrace. Now that we understand the birth of an aurora, let us explore the colors themselves. That celestial palette that has inspired artists and poets for millennia. While green remains the most familiar hue, appearing in perhaps 90% of aurora displays, the lights can paint the sky in an entire spectrum. Below the green curtains, sometimes a rosy pink or magenta edge appears. This comes from nitrogen molecules responding to the solar particles at lower altitudes, typically around 60 miles up. Nitrogen has two signatures. At higher energies it produces this pink or magenta glow, while at lower energies it can create a deep blue or purple. Though these colors are much rarer and harder for the human eye to detect, there's something remarkable about how we perceive these colors. Our eyes, adapted for daylight, don't see colors well in dim light. The rods in our eyes, which handle low light vision, see only in shades of grey. This is why to many observers standing beneath an aurora, the lights appear whitish or pale grey-green, like moonlit clouds in motion. But cameras, with their ability to collect light over longer exposures, reveal the full vibrancy. The emerald greens, the crimson reds, the violet edges. The aurora is always colourful, whether our eyes can fully appreciate it in the moment or not. The lights don't just vary in colour, they dance in patterns that scientists have categorized over decades of observation. There are arcs, those smooth bands stretching from horizon to horizon like ribbons suspended in the sky. There are rays, vertical streaks of light that appear to shoot upward or downward, following the invisible magnetic field lines. Corona formations create a spectacular starburst effect directly overhead when you're standing beneath an aurora, with rays appearing to radiate from a central point like the petals of a cosmic flower. Perhaps most dramatic are the curtains or draperies, those flowing sheets of light that ripple and fold as if blown by a celestial wind. These can pulse and wave with remarkable speed, sometimes shifting and moving faster than the eye can follow, other times drifting with the slow grace of fabric underwater. The movement we see reflects changes in the solar wind intensity and shifts in the Earth's magnetic field, a visible manifestation of invisible forces at play. The aurora follows a pattern across the Earth as well. There exists what scientists call the auroral oval, a ring-shaped zone centered on each magnetic pole, where auroras are most frequently visible. This isn't a fixed ring. It expands and contracts depending on solar activity. During quiet times, the auroral oval sits at high latitudes, around 65 to 70 degrees north and south. Cities like Fairbanks, Alaska, Tromsø, Norway, and Yellowknife, Canada, sit directly beneath this oval and can see auroras on nearly every clear, dark night during peak season. But when the sun becomes active, when a particularly strong burst of solar wind strikes our magnetosphere, the auroral oval expands dramatically. It can stretch as far south as 50 or even 40 degrees latitude during major geomagnetic storms. This is when people in Scotland, northern United States, and even occasionally southern England or the northern tier of the continental US might glimpse the lights. Though these lower latitude displays are typically fainter and appear closer to the northern horizon, time of year matters too, though perhaps not in the way you might think. Auroras occur year-round, day and night, but we can only see them when the sky is dark enough. In the far north, summer brings the midnight sun, when the sun never fully sets for weeks or months. During this time, even though auroras are happening overhead, they're invisible against the bright sky. The best viewing season runs from late September through late March, when darkness returns to the polar regions and the nights are long enough to witness the display. Even the time of night influences your chances. Auroras tend to be most active and visible in the hours around midnight, particularly between 10 p.m. and 2 a.m. local time. This is when your location on Earth has rotated to be in the magnetic tail of the magnetosphere, where particles have accumulated and are most likely to be funneled down toward the atmosphere. The lights don't follow a rigid schedule, of course, but over decades of observation, this midnight peak has proven consistent. There's also a fascinating rhythm that plays out over years. The sun operates on an approximately 11-year cycle, oscillating between solar minimum, when its surface is relatively calm with few sunspots, and solar maximum, when the sun becomes turbulent with many sunspots and frequent solar flares. During solar maximum, auroras are more frequent, more intense, and visible at lower latitudes. During solar minimum, they're still occurring, but they're generally confined to higher latitudes and are less dramatic. We're always within one phase or another of this cycle, this breathing rhythm of our star that has been measured and tracked for over 400 years. And here's something that still fills scientists with wonder. Despite all we've learned, despite satellites monitoring the sun and the solar wind, despite instruments measuring the magnetosphere, we still cannot predict with perfect accuracy when an aurora will appear or how intense it will be. We can see a solar flare erupt and know that particles are heading our way, but whether they lines create a spectacular display or a subtle glow remains partly in the realm of chance of the solar wind's mood, of how it interacts with our planet's magnetic shield in that moment. The northern lights remain, even in our age of understanding, touched by mystery. Let us continue a journey through their secrets. As humanity's understanding of the northern lights deepened, we discovered that we weren't merely passive observers of this phenomenon. We were part of a larger story, one that connects every aurora to the very structure of our solar system and beyond. In 1902, Norwegian scientist Christian Birkeland conducted a groundbreaking experiment. He created a miniature Earth, a magnetized sphere called a terrella, which he placed in a vacuum chamber and bombarded with cathode rays to simulate the solar wind. The result was stunning. Glowing rings appeared near the poles of his little sphere, mimicking the auroral ovals seen on Earth. This was the first time anyone had recreated the aurora in a laboratory, proof that the theory connecting solar particles and magnetic fields was correct. Birkeland's work was so ahead of its time that many of his contemporaries didn't fully accept it, but he had opened the door to modern auroral physics. What Birkeland couldn't have known was just how dynamic this system truly is. The magnetosphere isn't a static shield. It's constantly breathing, flexing, responding to every change of the solar wind. When a particularly dense or fast-moving section of solar wind strikes the magnetosphere, the entire system can undergo what's called a geomagnetic storm. The magnetic field lines compress on the day side and stretch even further on the night side, and enormous amounts of energy stored in the magnetic tail. Eventually, this stored energy is released in what scientists call a magnetospheric substorm. In a matter of minutes, the energy in the tail suddenly converts into the acceleration of particles, sending them cascading down toward the poles. This is when auroras suddenly intensify, when curtains that were gently waving become violently active, when the sky can appear to literally explode with light. These substorms typically last 1 to 3 hours, and multiple substorms can occur during a prolonged geomagnetic storm. Here is something that captures the imagination. The total energy released in a single auroral substorm is enormous, equivalent to a magnitude 5.5 earthquake, or about the energy consumption of the entire United States for roughly 2 hours. All of that energy, delivered from the sun, temporarily stored in our planet's magnetic field, then released as light and heat in the upper atmosphere. It's a humbling reminder of the scales of energy our planet routinely handles. And Earth isn't alone in this experience. The Northern Lights and their southern counterpart, the Aurora Australis, are not unique to our world. Any planet with a magnetic field and an atmosphere can have auroras. Jupiter, with its immense magnetic field, has permanent auroras at its poles that dwarf anything Earth has ever seen. These Jovian auroras are so powerful that they emit more energy in X-rays alone than the entirety of Earth's auroral displays across all wavelengths. Saturn, with its magnificent rings, also hosts auroras, as do Uranus and Neptune. Even more fascinating, some of the moons in our solar system have auroras. Ganymede, Jupiter's largest moon and the only moon in the solar system with its own magnetic field, has its own modest auroral displays. The relationship between Jupiter's powerful magnetic field and Ganymede's smaller one creates a complex dance of particles and light. We live in a solar system where these light shows are common, where the interaction between stellar winds and magnetic fields paints many worlds with color. But let's return to Earth for a moment, to the other half of the story we haven't yet fully explored. While the northern lights captivate the imagination of the northern hemisphere, the Aurora Australis, the southern lights, perform the same dance in the southern polar regions. These are not lesser siblings or pale imitations. They are the mirror image, occurring simultaneously with their northern counterparts. In fact, during a geomagnetic storm, the northern and southern lights are remarkably synchronized. Satellites orbiting Earth can photograph both auroral ovals at once, and the patterns are often eerily similar, near-perfect mirror images of each other. A bright arc appearing over Alaska will have its twin appearing over Antarctica at the same moment. This conjugacy, as scientists call it, reveals the fundamental symmetry of the Earth's magnetic field. Field lines that enter at one pole emerge at the other, carrying particles to both ends of our world. The southern lights are less frequently observed than their northern counterpart, but not because they're any less spectacular. The reason is simply geographic. The auroral oval in the south passes mostly over the Southern Ocean and Antarctica, places where very few people live. There are some viewing locations, southern New Zealand, Tasmania, southern parts of Australia, the southern tip of South America, but far fewer than in the north, where populated areas like Scandinavia, Alaska, Canada, and Iceland sit directly beneath the auroral zone. Those fortunate enough to witness the Aurora Australis report the same sense of awe, the same otherworldly beauty. The colors are identical, the patterns the same, the dance just as mesmerizing. Standing on a shore in New Zealand or Tasmania, watching green curtains shimmer over the Southern Ocean, seeing the same phenomenon that enchants viewers in Tromsø or Fairbanks, powered by the same solar wind, guided by the same magnetic forces, part of the same planetary system. There's a poetic completeness to this. Our planet adorned with crowns of light at both ends, connected by invisible lines of magnetic force, both responding in harmony to our star's breath. The Earth, it turns out, wears its connection to the sun like jewelry, visible to those who stand in the right place at the right time. Our understanding continues to deepen. As we moved into the space age, our relationship with the aurora transformed once again. No longer were we bound to observe from the ground, looking up at lights we could never touch. We began to venture into the realm where auroras live. The first spacecraft to directly measure the environment where auroras occur was Explorer 1, launched by the United States in 1958. Its instruments detected something unexpected: regions of intense radiation surrounding the Earth, trapped by our magnetic field. These became known as the Van Allen radiation belts, named after physicist James Van Allen, who designed the instruments. These belts are like vast reservoirs of charged particles, captured from the solar wind and cosmic rays, held prisoner by the Earth's magnetic field. They exist in two main zones: an inner belt beginning at about 600 miles altitude, and an outer belt from roughly 3,600 to 36,000 miles up. The Van Allen belts and the aurora are intimately connected. During geomagnetic storms, particles from these belts can be energized and precipitated down into the atmosphere, contributing to auroral displays. The belts are, in a sense, a storage system, a way the Earth's magnetic field captures and holds solar particles until conditions are right for them to create their luminous show. In 1996, NASA launched a mission that would revolutionize auroral science, the Polar spacecraft. For the first time, scientists could observe the entire auroral oval from above, watching it expand and contract, brighten and dim, as if looking down at a living thing. The images Polar sent back were breathtaking, the auroral oval glowing like a crown around the magnetic pole, pulsing with the rhythm of geomagnetic activity. These weren't just beautiful pictures, they allowed scientists to see patterns and behaviors that were impossible to detect from the ground. What these observations revealed was surprising. Auroras aren't just passive displays of light. They generate their own electromagnetic effects that ripple through the atmosphere. Strong auroras can create electrical currents in the upper atmosphere powerful enough to be measured on the ground. These are called auroral electrojets, rivers of electricity flowing through the ionosphere, the layer of the atmosphere that's been ionized by solar radiation and auroral activity. These electrojets have real-world consequences. They can induce currents in long conductors on the ground, power lines, pipelines, telecommunications cables. During the Great Geomagnetic Storm of March 1989, auroral electrojets induced currents in the Hydro-Quebec power grid so powerful that they caused transformers to fail. The entire province of Quebec lost power for 9 hours, leaving 6 million people in the dark. Auroras, it turned out, weren't just beautiful. They could touch our technological civilization in unexpected ways. This phenomenon is called geomagnetically induced currents, or GICs, and it's become a serious concern as our world has grown more dependent on electrical infrastructure. During intense geomagnetic storms, GICs can cause transformers to overheat, create harmonic distortions in power grids, and interfere with railway signals. Power companies at high latitudes now monitor space weather forecasts just as carefully as they monitor terrestrial weather, preparing for auroral storms the way coastal cities prepare for hurricanes. The auroras affect more than just power grids. Radio communications, especially high-frequency radio used by aircraft flying over polar regions, can be severely disrupted during auroral activity. The ionosphere becomes turbulent and irregular, causing radio signals to scatter or be absorbed entirely. Aircraft flying transpolar routes, the shortest paths between, say, North America and Asia, sometimes have to divert to lower latitudes during major geomagnetic storms to maintain reliable communications. Even satellites in orbit feel the aurora's influence. During geomagnetic storms, the atmosphere heats and expands, reaching higher altitudes than usual. This creates increased drag on satellites in low Earth orbit, causing them to slow down and lose altitude more quickly than expected. The very composition of the upper atmosphere changes during intense auroral activity, with increased atomic oxygen that can erode solar panels and other satellite surfaces. Space agencies have to carefully track auroral activity to predict when satellites might need orbital adjustments. GPS systems, which we've come to rely on for everything from navigation to precise timing in financial transactions, can also be affected. The ionosphere plays a crucial role of how GPS signals travel from satellites to receivers on the ground. During auroral events, the ionosphere becomes irregular and turbulent, causing GPS signals to take longer to reach the ground or to arrive via multiple paths. This can result in positioning errors of many meters, sometimes rendering GPS unreliable during the most intense geomagnetic storms. Yet for all these challenges the aurora presents to our technology, it has also taught us invaluable lessons about our planet's place in the solar system. The study of auroras has revealed that Earth's magnetic field isn't static. It moves, weakens, strengthens, and has even reversed its polarity many times throughout geological history. Evidence preserved in ancient rocks shows that the magnetic north and south poles have flipped at irregular intervals, roughly every 200,000 to 300,000 years on average, though the last reversal was about 780,000 years ago. We're overdue, in geological terms, though these processes unfold over thousands of years, not overnight. During a magnetic reversal, the field doesn't disappear, but it does become more complex, with multiple north and south poles appearing temporarily. If this were to happen in our modern era, the auroral ovals would behave strangely, perhaps appearing at mid-latitudes or in multiple zones. The protective shield that deflects most of the solar wind would still exist, but it would be reconfigured. It's one of many reminders that the aurora isn't just a light show. It's a window into the dynamic, ever-changing nature of our planet itself. And so we come to rest at the end of our journey through the northern lights, though their story continues endlessly above us. From the ancient cave dwellers who painted what they witnessed, to the indigenous peoples who wove the lights into their understanding of the spirit world, to the scientists who traced their origin back to the nuclear heart of the sun, the aurora has always been a bridge between earth and sky, between the known and the mysterious, between science and wonder. These dancing lights remind us that we live on a planet connected to forces far greater than ourselves. Every aurora is a conversation between our world and our star, mediated by invisible magnetic fields and painted in colors released by the very air we breathe. They occur whether we watch or not, whether we understand them or not, a constant reminder that beauty and physics are not separate things, but woven together in the fabric of our universe. As you drift towards sleep tonight, perhaps you can imagine yourself standing beneath those curtains of light, watching them flow and pulse across a darkened sky. The Aurora Borealis continues its eternal dance above the polar regions, born from the sun, guided by magnetism, made visible by the atmosphere, witnessed by anyone patient enough to look up on a clear, cold night. May these thoughts carry you gently into peaceful rest,